Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis, taken by Professor Krishna P. Kaliappan, Department of Chemistry, IIT Bombay. Myself, Sri Lakshmi, yes, I am the TA for this course. So, this is our 10th week tutorial session. So, in the last week, we have seen a discussion on up to lecture 39, as well as we have solved, I think, up to week 7 assignment we have been solving. So, today we will be starting with a discussion on this lecture 40, Swainsonen. So, before that, we will wait for a couple of minutes to see whether anybody is joining, and we will start with the session. Okay, so let's start the session with the discussion on week 9 lecture content. So, the first lecture of week 9, that was lecture 40, which was about Swain sonin. So, in this lecture, we have seen the application of stereo selective construction of tetrahydropyran in the racemic total synthesis of Swain sonin by Mukai and total synthesis of minus Swain sonin by Pearson using simple organic reactions with short and efficient sequence. So this Swainsonine is isolated from the fungus Rhizoctonia leguminicola, Swainsona chamescens, and Metarhizium anisoplie. So it is having three hydroxyl group and an intolycidine alkaloid. hydroxyl group, indolizidine alkaloid, mannose inhibitor, and anti-cancer drug. So that is the biological activity. It is a mannose inhibitor as well as anti-cancer drug. Other non-acid sugar inhibitors include homoalexine, homoaustralin, alexine, and australin. So Hashimoto's total synthesis was reported in 1985, where the key reactions involved nucleophilic opening of epoxide followed by the formation of a six-membered lactam in one pore. And the starting material used was D-mannose, which they converted into mannose diasteroid, and they used it as the starting material. And Collins reagent is one of the reagent which they used in their total synthesis, and they completed the synthesis in 12 linear steps with 4% of overall. Now coming to Pearson synthesis, which came out in 1996, the key step of the Pearson synthesis was sharpless asymmetric dihydroxylation and one-port reduction of acid and cyclization to substituted pyrrolidine. And the starting material used there was D-erythrose. It was completed in 12 linear steps with 19.6% of overall. Now, in Char's synthesis of Swainsonin, which came in 1989, the key reaction used was intramolecular 1,3 dipolar cycloaddition, stereoselective reduction of imine, and cyclization. The starting material used by Char's group was D-erythrose, and they completed the total synthesis in 6 steps with 21% of overall. And the other key reactions in that synthesis involves Wittig reaction, 1,3 dipolar cycloaddition followed by extrusion of nitrogen, and one port stereoselective hydroboration and reduction of lactam. Now, in Zhao synthesis or formal synthesis of Swainsonin, which also came in 1995, the key reactions were sharpless asymmetric dihydroxylation and kinetic resolution of alpha furfuryl amide. And the starting material used was furfuryl, and the key reaction was Akhmatowicz rearrangement, and they completed this total synthesis in 15 steps. So that's about Swainsonin. Now coming to the next lecture, which was about staurosporin. So here we have seen the application of intramolecular indole glycosylation in the total synthesis of staurosporin by Danishevsky. This molecule was isolated by Omura from Streptomyces staurocytes in 1977. And as we can see from the structure, it is having two indoles, this one, and one intolinol in the northern hemisphere and sugar moiety in the southern hemisphere. So it is known to have a nanomolar inhibition of protein kinase C, and it is having potential anti-proliferative activity. So the first oral synthesis of this molecule came in 1995, which was by Danishevsky's group, and the major synthetic challenge was the attachment of glycoside bond to each of the indole nitrogens. So the structure, whatever is given here, is not complete structure. And in Danishevsky's strategy for the containment of future N-methyl and O-methyl moieties in a cyclic framework, which provide chemical protection and offer stereochemical guidance for the intermolecular indole glycosylation. And the starting material used was dibromomalimide and L-glucose. And they completed this total synthesis in 28 steps from L-glucal and with 0.43% of overall yield. Then in Wood's synthesis, which came in 1996, which was an efficient divergent synthesis of pyranusylated indolocarbasols via a common intermediate. And they completed the total synthesis in 13 steps from methyl to diazo 3-oxobutyrate. and they use the key reactions like Moffat oxidation, tandem 3312 rearrangement protocol using R minus 1 non and 3 all as the source of symmetry. Then the overall yield of this synthesis was 9.61 percentage, and they also employed a successful ring expansion strategy to form the common intermediate, and from it they completed the total synthesis of staurosporin. So that was about staurosporin. Now the next lecture was about manzamin A, where we have seen the application of De-Mayo reaction, Pictet-Spengler reaction, retro-managed fragmentation, and managed reaction in the total synthesis of manzamin A. So the manzamin A was the first alkaloid isolated from the marine Okinawa sponge in 1986. And in 1986, Higa et al. And others isolated and confirmed the structure of manzamin A from marine Okinawa sponge haliclone. At present, more than manzamin alkaloids have been isolated from over 16 species of marine sponges belonging to 8 different families. Natural manzamin alkaloids, manzamin A N oxide, and 8-hydroxy manzamin exhibit potential anti-malarial effects. These group of alkaloids have exhibited diverse pharmacological activities like anti-cancer, anti-malarial, anti-leishmanial, anti-Alzheimer, antibacterial, antifungal. And in 1988, Wingler et al. First reported the total synthesis of mansamin A, and in Wingler's total synthesis, carbon was used as a starting material, which upon a De-Mayo reaction will give intramolecular De-Mayo reaction will give carbon camphor. And the key reactions used in this total synthesis were Pictet-Spengler, retromanaged, intramolecular managed reaction, intramolecular photocycloaddition reaction, and the starting material used were pyridine and 1,4-butane diol. Now, moving to the next lecture that was about progesterone, where we have seen the application of Stokes Eschenmoser's hypothesis of biomimetic polyolefinic cyclizations in the total synthesis of steroid progesterone. So, the basic skeleton of progesterone is given here, which is having four six-membered ring and one five-membered ring. Examples are cholesterol, ergosterol, pre-vitamin D3. In the most cases, there are two angular methyl groups also in the C10 and C13 position. So substituents on the same side as these angular methyl groups are beta substituents. Uh, Other examples include cortisol, testosterone, orgesterol, progesterone, estrone, cholic acids, and cholesterol. So in terpene biosynthesis, uh, so if there are 10 number of carbons, we call it monoterpenes, and an example is geraniol, which can lead to monoterpene. If 15 number of carbons are there, we call it sesquiterpenes, and farnesol can lead to sesquiterpenes. If 20 carbons are there, we call it diterpenes, and geraniol can lead to diterpenes. If 30 carbons are there, we call it steroids, and squalene can lead to steroids. So isoprene is a basic building block of terpene. In nature, isoprene exists as pyrophosphates, which are good living groups. Some examples for monoterpenes include limonene, menthol, camphor, carvone, geraniol, citronellal, pinene, verbenone, and nopal. So we have seen the biomimetic total synthesis of progesterone as well as Shor-Kirschen-Moser hypothesis, which means olefin geometry is preserved in the cyclization reaction, because trans olefin will always lead to transfused ring junction. Now moving to the next lecture, which was about steroids. Here we have seen the application of Marcus degradation process in the total synthesis of steroids like diosgenin, progesterone, cortisone, and testosterone, and these all were industrial methods also. So diosgenin is a drug which diosgenin is a drug. So in the drug discovery program, 1930s were considered as the decade of sex hormones. Molecular structures of male sex hormones, testosterone, female sex hormone, estrone, and pregnancy hormone, progesterone, were determined and used as drugs. So much attention was focused on progesterone because of its medicinal properties in the treatment of menstrual disorder. Unfortunately, the high cost associated with progesterone restricted its use as a drug. The cost of progesterone and other related steroids fell dramatically in 1940s with the creation of a Mexican company. Now we will see what is Marker's degradation process. So diosgenin in 1938, Marker from Penn State University proposed the correct structure for diosgenin, which is a plant steroid isolated from sarsaparilla. The side chain of diosgenin was initially considered as inert, but Marker could cleave that using a clever reaction. In 1944, Russell Marker achieved the first practical synthesis of progesterone from diosgenin. As the cost of this route is expensive, Marker started working at other sources to get diosgenin. In his search for better source of diosgenin, he appointed several botanists and launched plant collection trips in southwestern states of America. This low-cost process of making progesterone became useful in making the anti-inflammatory drug cortisone. In 1941, while going through a botany textbook, he saw a picture of Dioscorea that grows in Mexico. The root of this plant weighs about 100 kgs. In 1942, he went to Mexico by bus and took two bags with large roots of this plant and returned. Unfortunately, it was stolen during the bus trip itself. He bribed a policeman and recovered a 50-pound root to Penn State University. Back at Penn State, he could isolate diosgenin in satisfactory yield from this root. As this research program was funded by Park Davis, he approached them to commercialize this process. Not only they refused, other pharma companies also refused. He went to Mexico again, collected 10 tons of this root and talked to a local scale extractor and asked him to extract the root with alcohol and give the syrup. He gave him one third of the syrup and came to New York with the remaining. He converted this syrup into 80 kgs of progesterone. He sold 1 gram of progesterone for $80. He decided to form a company then to start this manufacturing, and he thought the best place to do would be Mexico. He found two entrepreneurs, Somlo and Lehman, and together they signed an agreement to form a new company called Syntex. In 1944, Marker then resigned from Penn State University and moved to Syntex. Now they could sell progesterone for $50 per gram. In 1945, there was a dispute in profit sharing, and Marker left the company. As he himself was doing the whole work with coding the reagents, the other two couldn't repeat the process. Marker moved out in 1946 and started a new company, Botanica Mex. He was with this company until retirement. Meanwhile, Syntex was looking for someone who will continue this work. They found George Rosengrantz, who received this work, and Syntex again started selling progesterone. He extended this work to other steroids like testosterone also. Syndex also later collaborated with Professor Carl Dejersey. He succeeded in converting diosgenin to cortisone. Existing Merck process took 36 steps to make cortisone. Upjohn and co-workers Upjohn and company invented a new microbiological process to oxidize progesterone, and the product could be easily converted to progesterone, which was 6 steps from diosgenin to progesterone, 16 steps from DPA to cortisone, and 16 from DPA to testosterone. So that was the about the lectures of week 9. Now, before maybe going to the next session, you can just quickly go through what I have been discussing so far. Then we will move into the discussion of some reagents and mechanisms which were uh, discussed in the lectures of week 9. Now, moving ahead with the discussion on some reagents and mechanisms which we have seen in the week 9 lectures. First one is Collins reagent. So Collins reagent is dipyridine chromium 6 oxide. So it is prepared from pyridine and chromium trioxide in DCM. It will give this dipyridine chromium dioxide. So it is basically reacting. It is basically used for the oxidation of alcohols into aldehydes or ketones, depending on whether the substrate is primary alcohol or secondary alcohol. And this is the mechanism of reaction. First, from this alcohol, this oxygen lone pair will attack over this chromium, and this bond will shift to oxygen to form this intermediate. Then one of the proton from this position will come over here, this will come over here, and this will move here. And this is not a general mechanism, like for every alcohols we cannot say like this is happening. But first step will be this oxygen lone pair attacking over this chromium and forming an intermediate. Then again, this proton from this oxygen is taken by this O minus of this uh, chromium, O minus attached to this chromium, and thereby giving this oxidized product. So this is the mechanism for this oxidation by Collins reagent. Now moving to the next reaction, which is Akhmatovich reaction. So Akhmatovich reaction is basically this ring expansion reaction, we can say. So here a furan ring is basically converted into a dihydropyran by using some oxidizing reagents. So this is the mechanism. If we are treating this furan compound with this NBS, it will form this bromonium ion here. Then with methanol, it will open this bromonium ion to form this intermediate. Again, this will hydrolyze like OMe can attack at this center. This double bond will shift over here, and bromide will leave to form this intermediate. Then hydrolysis can give this compound, which again cyclization will undergo to form this dihydropyran ring, starting from the dihydrofuran ring. Now the next reaction is sharpless asymmetric dihydroxylation, where this alkene is converted into a diol by AD mix alpha or beta, water and tertiary butanol. So this can be done in a stereo selective way, that is the speciality. So depending on which compound we are using, we can change the stereochemistry of the diol form. So either we can use DHQD twice PHA or DHQ twice PHA. So this is the mechanism of this reaction. So if it is AD mix alpha, it will be giving from this phase, and we will be getting this kind of stereochemistry. And if it is AD mix beta, it will attack from this phase, and we will be getting like medium group phase, and we will be getting this product. So the reaction starts with this osmium tetroxide. So this osmium tetroxide firstly coordinate with this alkene to form this compound. Then what is happening in the presence of NaOCl, NaCl will eliminate, and this oxygen will get inserted in this compound, and then again another alkene will react with it to form this intermediate. Again ligand will come and form this diol. So that is happening with the mechanism. So in the first cycle also we are getting diol, and then in the second cycle also we are getting the diol. So this first cycle can have high enantiomeric excess rather than compared to the second cycle through this intermediate. Now the next reaction is Fitzner-Moffat oxidation, which is the oxidation of alcohols into the corresponding aldehyde or ketone by using DCC, DMSO, and acid. So here is the mechanism. Firstly, DCC. So DCC will get protonated, and in the presence of acid or which source we are using, then DMSO, this oxygen lone pair, will attack over this carbene. This bond will shift over this nitrogen to form this intermediate. Then our corresponding alcohol lone pair can attack at the sulfur position and form this intermediate. Then base will take this proton. This bond will shift over here, this will shift over here, and this will shift over here to form this compound. Then this nitrogen lone pair will take this proton to form this intermediate, and then DMS, dimethyl sulfide, will be leaving to form the oxidized product. So that's the mechanism of Fitzner-Moffat oxidation. So the next is Pictet-Spengler reaction. So Pictet-Spengler reaction is the cyclization to form this kind of compound. So this nitrogen lone pair will first attack at this carbonyl carbon to form this intermediate. Then this water molecule will leave and form this iminium ion, and then this aromatic ring, that carbon will attack over this carbon, and then cyclization will happen to form this ring. So that is known as iminium ion. This detailed mechanism is given here as well. Now we will start the discussion on week 8 assignment. So the first question is, identify the major product in the following transformation. So this compound upon treatment with this orthoformate and this acid and heating, which will be the major product out of the four options given here. I'll give you some time to think about the mechanism of the reaction as well. So here the correct answer is option D. And what is happening? This orthoformate and this acid in the presence of heat will attack over this alcohol and form this intermediate. So firstly this will form, and then a Claisen rearrangement 3,3 sigma tropic rearrangement will happen to form this compound. So the correct answer is option D. Moving to the second question, what is the major product in the following transformation? So this compound upon treatment with this triphenyl phosphine in carbon tetrachloride and triethylamine, which will be the major product here? So here what is happening, this nitrogen lone pair will come and attack at this carbon, and this OH will be converted into chloride by the CCl4 and it will be eliminated, and then this nitrogen lone pair will attack over this carbon and the chloride will leave to form this product. So the correct answer will be option C. Now, the next question, identify the major product in the following transformation. So, this compound upon toluene reflex condition, which will be the major product formed. So here the correct answer is option A. And what is happening under toluene reflex condition? This oxygen lone pairs of this carboxylic acid will undergo this imine carbon and form this pyrocenter. Then further it will rearrange. That is this bond will be breaking and this group will attack over this nitrogen to form this compound. So the correct answer is option A. Now the next question, match the following structure with suitable names. So four structures are given and four names are given: disomorphin, codeine, thibane, morphine and galanthamine. So try to identify the structure of each of this natural product. So here the correct answer is option D. That is, the first structure is for morphine, then the second structure is of galantamine, and the third structure is of first structure is of morphine, second structure is of galantamine, third structure is of codeine, and fourth structure is of thibane. Now the next question, identify the transformation occurring in the following reaction. So this compound upon treatment with this potassium ferricyanide, water and sodium bicarbonate, this reaction is happening and this compound is forming. So which reaction is that? Diene phenol rearrangement, open or oxidation, oxidative phenolic coupling, or Kulinkovich reaction? So here the correct answer is oxidative phenol coupling. And what is happening here? Firstly, here in the presence of this potassium ferricyanide, this oxygen OH will leave, like oxygen hydrogen bond will break, and here O radical will form, and here also O radical will form. Then this aromatic carbon carbon bond will break to form these two radicals. So here it will be double bond O, here it will be double bond O. Then this radical will combine to form this intermediate. Then again, this aromaticity will be retained and this ketone will be converted into the corresponding phenol. And then what can happen? This oxygen, so once this aromaticity is retained, this oxygen lone pair can attack over this center. Then this will come over here, this will go, and this bond will only be remaining, so giving this product. So the correct answer is oxidative phenol coupling. Now the next question is identify the major product in the following transformation. So this is also another similar reaction. So this compound upon treatment with this potassium ferricyanide, K2CO3, toluene in water, which will be the major product here. So here the correct answer is option C. What is happening here? So firstly, this will be converted into the corresponding. This formyl group will come over this nitrogen by using this formate ester and this formic acid. Then in the presence of this K3FeCN6, as we discussed earlier, this oxidative like this oxidative phenol coupling will take place to form this product. So the correct answer is option C. So here directly we are starting with this one. So the oxidative phenolic coupling is taking place to form this compound C. Now the next reaction, identify the major product formed in the reaction given below. So this compound upon treatment with this AlCl3 and CS2 in reflex condition, which will be the major product here. So here what is happening, firstly from this acid chloride, this is a Friedel-Crafts type of acylation reaction using this aluminum chloride. So this group is attacking over this center, and chloride will leave to form this compound. So the correct answer is option B. This is an example for Friedel-Crafts acylation. Now the next question, identify the major product in the following transformation. So this compound upon treatment with this SnCl2 2H2O, which will be the major product here. So here what is happening, in the presence of this SnCl2, this group will be leaving, and then the cyclization will happen to form this compound. So the correct answer is option C here. Now the next question, identify the major product of the following reaction. So this compound upon treatment with LAH, CBr4 and PPH3, first LAH and in the second step with CBr4 and PPH3, which will be the major product here. So here first LAH will reduce this ester into alcohol, and CBr4 PPH3 will convert it into bromide. Appel reaction. First is reduction of ester and second one is Appel reaction. So the correct answer is option A. Now the last question of week 8 assignment, identify the major product in the below reaction. So this compound upon treatment with H2PDC in ethanol under 30 psi pressure, which will be the major product here. So here what is happening, this H2PDC will deprotect the CBZ group, so it will be free NH2. That free NH2 will first attack at this epoxide center, and epoxide will be open to form this intermediate. Then again this free NH can attack at this carbonyl carbon, and this lactam formation can take place to give this compound. So the correct answer would be option D. So that's all about today's session. We have discussed the week 9 lecture contents as well as week 8 assignment. And we have also seen mechanisms associated with several reagents and several named reactions as well. So thank you for joining. If you have any questions or any doubts, please do let me know by the next tutorial session. So see you in the next tutorial session. Thank you.